Okay, good morning, class, or afternoon, or whenever you're watching this. I'm going to be working from day 8 handout on my website on Unit 3. And what we're going to talk about is hydrated ionic compounds. And we're going to look at the formula first. I'm going to use pink. So this is an example of a hydrated ionic compound. You see that we have barium chloride, and with it comes two waters. Waters are what make this compound hydrated. Okay, so I would call this barium chloride dihydrate. And let's have a look at what it actually looks like. So, this is trihydrate. I don't know where I got this image. Oops. Oh well. Okay. So if we're looking at the actual ionic compound, this right here is the ionic compound where you have barium and two chloride ions are forming an ionic bond because of electrostatic attraction. But then, as you can see, over here, the negative dipole that's found in oxygen is being attracted to the positive dipole of barium. I'm sorry, I have the sniffles as well. This chloride, because it's negative, it's an anion, it's going to be attracted to the two positive dipoles of water. So this should actually be trihydrate, if this image is correct. I just got all this from Google, I'll be completely honest. So when I ask you, why do ionic compounds form hydrates? You can say that it's the electrostatic attraction that occurs between anion and cation has the same attractive force between ion and dipoles. So the barium positive ion, the barium cation, has an ion dipole interaction between the oxygen in water, the negative dipole. And the chloride anion has an electrostatic attraction with the positive dipoles of water found in hydrogen. So which type of intermolecular bonds are formed? These are called ion dipole interactions. And we have water that's floating around in the atmosphere. Could be, you might be thinking, oh, it's rain, but it's also humidity. Okay, so people with curly hair, you guys know that when it's very, very humid in the summer, our hair gets a lot curlier because we pick up a lot more water, whereas in the winter it's a lot drier, our skin gets dry, things like that. That's all based off of humidity. Well, these ionic compounds, they pick up on that humidity as well. So how can ionic compounds how can hydrated ionic compounds be separated from the anhydrous compound? Well, if you remember the melting point, or let's do boiling point of ionic compounds is very high, and water is 100 degrees Celsius. So we heat the sample to say like 200 degrees Celsius. All the water boils off, and only the ionic compound is left. Now, I want to introduce a new word, only the anhydrous. Whenever you see an, that means opposite or without. So anhydrous compound is without water compound. So if you get the sample up to 200 degrees Celsius, all that's going to be left over is just simply the ionic compound. So we would have done this in class. Let's take a sample and determine the hydrated ionic compound of copper 2 chloride using the following information. Okay, so the sample before heating, we have in here, I'm going to draw it, okay. In my crucible, I have, oops, I don't want to put that there. I have 38.11 grams of hydrated copper chloride. Then I'm going to take a Bunsen burner and I'm going to heat it up to, I don't know, at least 200 degrees Celsius. I actually don't even know how hot the Bunsen burners get. I should put something, or I should try to test that out. Afterwards, it doesn't change color. It changes color a little bit. Let's do, actually goes like to this gray color. The mass of the sample after you've heated it is 33.61 grams. So think about what is going on. Well, the sample before heating, the 38.11 grams, what this represents is the ionic compound plus water. And then the 33.61 grams represents just the ionic compound. So if we find the difference between 38.11 and 33.61, which I get 4.50 grams. So do you see how there's two decimal places? When you subtract numbers in scientific notation, you keep the number of decimal places. So even though I got 4.5, I'm putting 4.50. This represents the amount of water. Okay, that's the difference. And what was lost? The water was lost. Let me get rid of my terrible graphic. And let's calculate. What color do I want? Pink. So what I'm going to do is I'm going to take, I know what my formula is. It's copper 2 chloride. So copper 2 chloride is this. And I have water. Now, when I calculate the hydrates, I set them up a little bit different. I put the numbers as coefficients. Okay. So now what I'm going to do is I'm going to divide these by their respective molar mass. So for water, it's 18.02. I don't even have to look at the periodic table. And for copper, let's see, I have 63.55 plus 35.45 times 2. I get 134.45. And now I do the division that is represented. So for copper chloride, I get 0.2499. I'm going to round it to the nearest decimal. So 0.25, I see in my head a quarter, right? 25 cents, quarter. And then 4.5 divided by 18.02, I get 0.25. Again, well, 0.249. So because they're equal to each other, if I multiply both numbers by 4, which you're allowed to do, I'm going to just get a whole number. Just going to get number 1, or sorry, coefficient of 1 for both of them. So how would I name this? This would be copper 2 chloride monohydrate. So let's try one without the table, without the schematic of the lab. A 50-gram sample of hydrated barium hydroxide contains 27.2 grams of barium hydroxide. Calculate the percent by mass of water in barium hydroxide, whatever hydrate, then find the value of X. Okay, so we have some numbers. We have 50 grams is barium hydroxide, whatever hydrate. We have 27.2 grams, which is barium hydroxide. Well, the difference between it, so what's that going to be? 22.8 is water. So when it's asking for the percent of water, what we're going to do is we're going to take 22.8 grams divided by 50 grams times 100%. Because we want to know out of the actual total, what's that, 45.6% is water. Let me make sure that it's early on a Sunday morning. Yeah, okay, my math is right. So we know that in the hydrated sample, 45.6% of its weight comes from water. Okay, now let's figure out what the X is. So I'm taking my mass and I'm using them as my coefficient. So remember, this is different than calculating the molecular formula because I'm making them coefficients, not subscripts. I'm dividing it by the molar mass. Let's calculate barium hydroxide. So barium is 137.33, it's a heavy metal, plus two hydrogens, so that's 2.02, plus 2 oxygens, which is going to be 32, and I get a total molar mass of 171.35. So 27.2 divided by 171.35 is 0.159. And for water, 22.8 divided by 18.02, I get 1.27. Okay, so this looks ugly. What are we going to do? Well, we're going to divide both sides by the smallest number. And let's see what happens. Well, we know that 0.59 divided by 0.59, that's 1. And 1.27 divided by 0.159, I get 7.95. What am I going to round that to? 8, H2O. Okay, so I would say that this is barium hydroxide octahydrate. Okay. Okay, so that's the whole lesson there, and I know that students generally have difficulty with this, so I gave some questions here that are just example questions. I'm going to work through a few of them. These are not what you're going to hand in, so you can change to what you want to hand, or you can start working on what you want to hand in, or you can pay attention and I'll go through some more of the examples. Okay? Oh gosh, I'm so sniffly, I'm sorry. Let's do, looking at this. I'm going to do number 7 for sure, and then I don't know, let's do number 4. Okay, so number 4, a sample of hydrated sodium carbonate. So we know that sodium is N plus and carbonate is CO3, 2 minus. So it'll be Na2CO3. Has a mass of 8.85 grams. It loses 1.28 grams when heated. So you have to be able to take apart that information. The hydrate is 8.85 grams. And then there's going to be 2 different entities. There's the anhydrous amount, and then there's going to be the water. And it gives us the information in the question. It loses 1.28 grams. That's the amount of water. And when you subtract those 2 numbers, this amount, 7.57 grams, that is the anhydrous amount. It's these 2 that you use to form your calculations. And 7.57. Okay, this piece of information here, it's not really useful other than finding out how much water and how much anhydrous is left. Okay, so as always, we'll divide that by 18.02. And then let's go to our periodic table. 22.99 times 2 plus 12.01 plus 3 oxygens is 48. And so I get a total of 105.99. And so I get a very tiny number for this. And that's okay. Because, oops, oh dear. Look, it's a 1-to-1. So I know it's a 1-to-1 because they're exactly the same numbers. So I know that it's another monohydrate. Okay. Now, the reason why I'm doing number 7, and a hydrate is determined to be 45.43% water and 54.57% cobalt chloride. Find the chemical formula and name for this hydrate. And it says, hint, assume that there is 100 grams because you're dealing with, it's very similar to like molecular formulas. So it's cobalt chloride and water. And again, we're assuming we're going 45.43%, 45.43 grams. And then the rest is 54.57%, 54.57 grams. Divide this by 18.02. Divide this by, okay, well, we got to go to our periodic table. Cobalt is number 27, 58.93, plus 2 chlorines, 35.45 times 2, and I get 129.83. When I divide these, I get 0.420 here, and I get 2.521. My next step is going to be divide both by the smallest number. This is a cobalt chloride is going to be coefficient 1. And water will be 6. So it's cobalt. Cobalt is multivalent, right? So cobalt 2 chloride. And then 6, it goes mono, di, tri, tetra, penta, hexa. Hexahydrate. Et voila. Let me know if you have any other questions. Again, the biggest takeaway is make sure that you use coefficients now instead of subscripts like what we were doing with molecular formulas. And you should be good. And I think this takes us to the end of chapter 6. Woohoo, you guys are doing it.